Yep. Like if Luis can join out, yo.
Yeah, and Carlos needs the link too.
I think it's a different link. The one in the URL is different. Felipe, you maybe need to grab a new link for us. Maybe a live link. I don't know.
Okay, I have three links here: event page, YouTube page, and a video embed.
You know.
What's so funny, Andres?
The e-commerce room, George Clooney eating a hot dog.
Can we start now?
Trader Joe's milk chocolate jumbles. Nom, nom, nom. Go ahead, start.
Okay. So I made some slides to guide my presentation to help you understand me better. And this lunch and learn is about traveling salesman problem. And I will follow the order of the slides, but feel free to stop me anytime to make a question or anything else. And let's start with the concept of this problem. So the traveling salesman problem, by definition, it's a given list of cities and distance between each part of cities determines the shortest possible route that visits each city exactly once and returns to their origin. That is the definition of the problem. It's applicable to planning systems, logistics, the manufacture of circuits, DNA sequence, somehow. It's formulated in 1930 by Carl Menger, and it's considered an NP-hard problem. It means that it can't solve in polynomial time, and that's it. In summary, there is no way to get the optimum result in polynomial time. We can solve the problem with a possible route that connects all its cities, but to ensure that the route is the optimum, the best choice in our available choice, we can't do that in polynomial time. So let's see how to represent this problem. The TSP can be represented as a graph, like in this image. We have an example of this problem, where the cities are the vertices, the roads are the edges, and distance are the weights of the wedges. The wedges. Sorry. So TSP is considered symmetric if the distance between the cities are the same in each opposite direction. It forms an undirected graph, and is asymmetric otherwise. So we can represent that with a directed graph. So that's the image that best fit this problem. By the concept, we need to choose a a city to start. We need to visit the other cities once and then get back to the origin. So there are some solutions for this problem, but what about you? I want to hear from you. How would you solve that problem? So if anyone has any idea of how to do that.
I would ask David to solve for me.
That's a good. I would ask Google. Um, yeah.
Any
I don't
idea?
know.
Okay, it's basically the math concept of this problem is a big combination of numbers that forms the shortest path. Let's see what the solution I propose to this lunch and learn and how to optimize that. So the basic solution for the TSP is using backtracking. Backtracking, also known as brute force, will make all possible combinations and choose the best from choose combinations. So basically, we need to enumerate the candidates, where in this case are the vertices, and compute all solutions. So we need to get all paths starting from the vertex 1, all paths start from the vertex 2, and etc. etc. And one method that some people use to punish infeasible paths is determine big distance, huge distance, where to represent roads that do not exist. So getting back to this example, we don't have a road direct from the city 1 to city 3. So we can fake that with a huge distance to don't get a good path using this road once it not exists. Let's see. Let's get backtracking. Okay, the complexity of this algorithm is big O of n power n plus 1, where n is the number of vertices. It means that it's a lot of combinations. I made a small solution to show this problem in practice. So I created. Are you seeing my text editor?
Yes, it's sublime. It makes me sad.
Okay, so I created a small data structure to represent the graph. I choose to represent this graph using classes instead of metrics of adjacency because it's easier to understand, but it's not a better performance. But anyhow, so we have a graph with a collection of vertices, and each vertex has a collection of edges. So I also have some data files here that have examples of a sample of valid graph for this problem. So come back to my keynote here. This image represents this sample here. So we have 11 vertices and a lot of edges according to this image. The solution of the solver of this problem basically has a backtrack method that calls it recursively and construct the candidates and do the path. Let's see that in action. I will print the path to get to show the number of complete paths that this will generate. I will choose a small sample of that because it's a lot of files, and let's go. So it's made all possible combinations of these vertices, and starting from any point percurring all other cities and getting back to the origin. In this case, it's a very naive backtracking. It has no restrictions. It constructs all possible combinations. And here, I measured some things to compare in the future, and we had 40 valid paths and a lot of complete paths that's not possible to do. And the minimum distance is 15, and this is the shortest path. So what's the problem with this approach? We have a lot of paths that's not valid. So it's we wasting a lot of computational resource to create impossible routes. So let's think about that and see how we can improve that. So we need to start running. We know that we have impossible routes. We are considering impossible routes, and also we are revisiting some vertices. In this case, cities, and it's not possible. The problem says that only all cities should be visited once, and we need to get back from the origin at the end. So this is the start point to do some optimizations. Let's see here in this code. So this method is where the magic happens. It's construct the candidates that we use to create the possible solutions. So I will comment this line, and instead of return all possible paths as a candidate, I will return only the unvisited path, unless that is the last step, because in the last step we need to go back to the origin. And let's see how it will affect this program. No, I'll comment this compare and just a minute. Let me get back to the start point, run it again. Okay, so do the small optimization here. So let me see here. We have exactly the same result here. The minimum distance is the same. The shortest path is the same, but we have a lot of much fewer paths to analyze. And this small improvement to do not visit already visited places or cities make this the complexity of this algorithm from exponential to factorial. That's not good. It's still not good, but it's a little better. Let's see here. Compare the elapsed time is much quicker. Although we have less paths per second computed, but it's not a problem because we are only considering better options. And let's go back to Keynote. So this what we did here: remove the visited cities from the candidate, and it's improved a little. So another optimization that can do here is consider only feasible paths. I mean, if I can't connect city 1 direct to the city 3, I can't. I don't need to consider this as an option. So I will do a small change here. From if the solution is starting, if we are in the start point, we can start from any city. If not, unless it's the last step, we will consider only the unvisited. No, sorry. If this last step, we need to reject the visited places here. No, it's wrong. Let me. It's not so good. Actually, we need to invert this. Solution, but first. If solution back to origin. Okay. Otherwise, we need to return all the possible routes from the current point that's not visited yet. Let me do that. I'll reject the. That's it. That's it in practice. No, it's still not the best option, but it's a small improvement of the previous code. Let me check here. No, it was right. So there it is. Getting back here, you want to consider it as candidate the roads that are connected to the current paths and already not visited. It is still not visited unless this is the last step, because in the last step we need to get back to the first step. Okay, so that's it. This change made a huge improvement compared to the previous one. It's not a factorial time anymore for a graph with 5 vertices. We had a 40 complete paths. All of them are valid. So and their running time is faster. Let me. I will rerun those samples, those tests with another sample, with a big sample here, the same that I used it on the keynote. Back to the first one. So this solver is limited to 10 seconds for the presentation purpose. So I will do a bigger sample with the naive backtracking and see what happens. So the naive backtracking uses a complexity of exponential time, and the solver aborted and because the time limit was exceeded, and its solver with the naive backtracking was not able to solve this problem. We have analyzed a lot of paths, but without any success. Let's do the first improvement here and compare again. So it also stopped by the time, but now it could reach a solution. We can't claim that it's the best path because this solver didn't analyze all paths. So it was possible to encounter a better path with it didn't stop the process, but it's an improvement. So for 11 vertices, we have a minimum distance and the shortest path, but with a very low accuracy. Let's do the last improvement and see what happened again. So the time is very, very, very faster. We have a confirmed shortest path because we analyzed all possible paths and with a 100% accuracy. It's a big improvement comparing the choose tree approach, but it's not a good solver for this problem because we have a really larger instance for this problem that we can't solve. I have here a sample with 70 vertices that even with our best solver, we can't reach any valid path. Let me do that to show to you guys. There are a lot of improvements that we can do to solve this problem. I will talk a little about this, but I was liking to show to you how to even every improvement has difference in this size of problem. So for my larger instance, the solver could not find even a solution, not the shortest of all, but no solution. See here, I have commented this line here to show how some small changes here made a huge difference here. In this line, we check if the current vertex connects to some places. I do that using a hash table because it's a little faster. We could that also using the include method to show that the label that I'm looking for, it's present in the edges. I will run the larger sample again to show here. I'll need to do that with the smaller solution because we need to compare the paths per second. Let me do that with using include. So we could analyze more from the 4,000 paths per second, and if we change that to hash table, let's see how many. It's not true. Let me do that again. 2 times. So it's about 4,000, and for using hash table, it's pretty the same. It's not make a big difference here. We need to do with a real benchmark using more instance. In the test I made before, that presented a better result. But in this solution, I choose to use hash tables on all the graph structure because it's faster to access. So let me get back to the keynote here. So I enumerated here other possible optimizations we can do to solve this problem. One common way to solve that is using a lower bound and an upper bound. We can define a lower bound as the minimum distance to solve this problem. Even with the minimum distance, it's not a feasible path. It's just because in some cases, let me try to practice here. In some cases, let's suppose if you start from city 1 to city 4, 5, 2. We can't get back to the city 1 anymore. So this path is ended. There is nothing else that we can do in this case. In this case, the minimum path of this subgraph here is much lower than the needed. As example, we can consider as the minimum as the lower bound here the sum of the minimum edges. So we can ensure that the shortest path has not less distance than the sum of the minimum edges. So we can use this as a lower bound, by example. And for the upper bound, we can define a maximum distance to abort the solutions that are already exceeded this maximum distance. The upper bound could be obtained from the best partial solution, or a grid algorithm that gives a good solution but not the best one, or approximated algorithm that solves the TSP. We have approximated algorithm that solve it with at the maximum of 2 times the optimum size. So we can tie these bounds to improve the performance. Do you guys have any question?
Yeah, so do you know, like this is unrelated to this, but it reminds me a lot of an older problem, which, like, so this, I was reading about this traveling salesman problem. I mean, when I added it to the Lunch and Learn, I had read about it, and I think it was developed in 1930, but then there's a much older problem in mathematics, the Seven Bridges of Königsberg, which is like 200 years older, and it's kind of laid the foundation for graph theory. I guess I just have like a question for you, just a curiosity. Did you know about the traveling salesman problem before you decided to talk about it?
Yes, I had to solve some assignments of the master's degree using almost the same solution I presented to you.
And is it related to, like, do people talk about it as a relation to graph theory, or is it more about computational complexity? Like, what is the domain of the traveling salesman problem?
No, it's all about graph theory. There are a lot of techniques and improvements about graph theory that you can use here. Let me try to see here. Graph theory. I choose to use vertex class and edges as object to make the code easier to understand. But the best way to solve that is using adjacency matrix that represents the column of the vertices, and the rows are vertices and the color are vertices too. So let's see if we have the concrete example here. Let me write one. If we have 3 cities, I suppose, and there is no path from 1 to 1, that's obvious. That 1 to 2, that from city 1 to city 2, we have a distance of 3, for example, same here. So it's an adjustance matrix. It's much faster to check if start from some point leads to the other point, or to do some mathematical operations to get uh, some answers I think the name is Hamilton cycle that determines some information that's important to solve this problem. There are a lot of to use from math here and from graph theory.
Cool. And then, like, the other question is, can you just summarize? Oh, sorry. Can you just summarize the like the improvements you made? Because you went from basically like the solution was polynomial to factorial to like, so just like the improvements that you made for like the you know, the number of permutations that you had to go through in order to solve the problem. Can you just summarize like what the improvements were like called again?
Yes.
Do you understand? Yeah.
Yes, I think I got it. Let me get back here. So in the first example I wrote from any point we get a list of the all verts as a candidate. It will generate an answer for 5 vectors and options like this, paths like this. That's invalid. That's invalid. Etc. And you know, for this domain, for this problem, when we have some requirements, like the first step must be equal to the last step. We can't visit the same seed more than one time. So what I did here is some small improvements to meet those requirements. For example, here for the last step, I return as candidate only the first step. It means that we won't analyze invalid solutions from the last step. And here, the second improvement I did, reject the visited place, but it's not all, because we are still considering vertices that are not connected to the current. Example, get back to the keynote here, that image. If we are on the city 1 and we like to go to the city 3, we can't go directly from there because it's no road, and the second improvement are not considering these roads. That's because it's puts a lot of invalid paths. But it's better solution, so all unvisited. Better from return all verts. So in the first one, I return as a candidate all options. In the second version, I return as candidate all unvisited options, and in the last one, I return all unvisited roads that are connected to the current one. It's some kind of silly to explain that, because it's obvious to this problem. The definition says exactly that. On city, the city should be visited only exactly once, and then at the last point, the person or anything should get back from the start point. So what I did here is a better way to attain this problem. The first version here, it's the purely a backtrack implementation. It's a naive or full implementation of backtracking. So we'll try all solutions, no matter if it's a valid solution or impracticable solution. The second one, it's a middle term here because it was considering only unvisited places. And the last one, unvisited places that are connected to the current edge. Basically, that's what I did here. It's a small improvement because it's some kind of obvious for this problem, but get a very better results.
All right. I don't have any other questions. Does anybody else?
Andreas, I think that's the same guy, the Austrian economics.
Actually, I don't think so.
Because I had in when I was creating this presentation that this problem was introduced in Vienna University, so I think it could be some related with the person you mentioned.
All right.
So in HPB, we are using backtracking to solve the construct satisfaction problem that we use to mount the display tiles of the home page, and basically it's the same approach that I presented, but some difference because the construct satisfaction problem stops to process when it found a solution, not matter it's the best or it's not. So when we have this scenario to stop the solution, we can do a lot of improvements on in this case I presented, on the candidates to get easier to engine to find a solution. This technique doesn't matter in this concept of DSP because we need the shortest path, not a path. But I think it's important to mention that you are using some kind of close approach on our product.
Cool. This was good. Yay. These are the kind of problems that made me interested in like just math and computer science in general. Like I went into philosophy because I liked the more theoretical side of the problems than the practical side. You know, the solutions once you get at, and this doesn't have like a perfect solution, which is why I think it's an interesting problem. There's a lot of different approaches to it, but it remains interesting because not all solutions are equal. So, it's a cool problem.
Yes, the same for me. I'm not very good with math, but this kind of problem makes me study it more to try to solve things like that.
Yeah, I mean, I learned about this problem because I was watching a presentation on graph theory about like, it wasn't on graph theory, it was just teaching math. And when they were going through the history of math, and I've been reading 2 books on math, they got to, you know, the 7 bridges of Königsberg. And then I found about the traveling salesman problem as well. And I think it's good, it's kind of interesting to sort of trace the history of the problems to see, you know, like, what people were thinking about and trying to solve that led them to, you know, these problems. Because the traveling salesman problem is popular in computer science, but it predates computer science by, you know,
Yeah.
quite a few years. So, Okay. Well, I don't have anything else. If nobody else does, I just want to say thank you.
Hey Felipe, can you send the GitHub link for the fire solution?
Yes, I will submit it to GitHub today. It's only local now, but I will do that.
Okay, thanks.
Thank you all, guys.
Thank you. See you guys later.
See ya.
Yeah.